Let's continue our discussion. So, before moving further, let me summarize the things we have discussed already in the previous video. So, we have discussed about rigid body and motion of rigid body. So, a rigid body is something having fixed shape and size. We have discussed this thing, and it means this rigid body, the particles constituting this rigid body are not going to change their relative position. So, we can say this rigid body is a kind of system of particles with fixed relative position. Yes, it means if you are choosing a particle as a reference particle, all other particles will be at a particular position with respect to this reference particle, and during its motion, this relative position or these positions are not going to change. Okay, now motion can be pure translatory. For example, a wooden block sliding over a horizontal surface here, and this wooden block is moving from one point to another point. This kind of motion is pure translatory motion. Okay. Now, what about this body? A spherical body rolling over a surface. So this body has translatory motion as well as rotation. And now you can see the particles in this body are moving on a circular path around this axis, which we call axis of rotation. So here we can see that this body has both translatory and rotatory motion. Now do pure rotation kind of thing. We can see here in this ceiling fan, if the ceiling fan rotates about this axis, which is passing through its center. So here this body is not being displaced, or this ceiling fan is not moving from one location to another. So this is a kind of pure rotation. Now pure rotation can have two different forms here, one with fixed axis, another with rotating or oscillating axis. Okay, I'm giving example. Fixed axis, here we have in front of us. This is an example of fixed axis rotation. Now, what about this top? Let's say we have a top here, and this top is rotating about this axis, and this axis itself is rotating about this point in this particular circle. So, such a motion of axis here, this motion of axis we call precession. Okay. So center of mass is kind of concept of making equivalence where suppose there are many point masses here, and if we want to choose a single point mass which can produce the same effect as these point masses are producing altogether, so that point mass will be called center of mass, or more precisely the location of that point mass is the center of mass. Okay, okay, take this scenario. Let's say this is y-axis, this is x-axis, and we have two masses here. Here we have one mass, let's call it m1, and here we have another mass, let's call it m2. And then this is our reference point, and this mass is at location x1, and this is at x2. Now, if we want to know what is the center of mass for this system containing these two point masses, so let's say the position of center of mass is somewhere here, and this is x center of mass. Okay, so how can we find out what is the value of this x? So what is concept for this center of mass? There is a point mass which is producing an equivalent type effect for these two point masses. So if we want that what will be the m1 into x1 plus m2 into x2, it should be something m1 plus m2, these two masses combined multiplied with this position xca. So here we can say that center of mass is located at this position, which can be find out if we know what are the masses m1 and m2 and their positions. So it will be m1 x1 plus m2 x2 divided by m1 plus m2. Okay, this is for two masses. What about there are n mass such masses spreading over this line along x-axis only for timing, let's say. So for n such masses, we can write x center of mass will be the same argument. We are going to extend m1 x1 plus m2 x2 plus and at last for the nth mass and whole divided by m1 plus m2 plus m3 and so on up to mn. And if we write it in short way, we can say using summations I equals to 1 to n and mixi whole divided with this one I equals to 1 to n mi. Okay, this is for one dimension only if these masses are along a single line. Okay, now what about if these point masses are in two dimensions, means they are scattered in a plane. So in that case, we can just extend our argument that there will be a new coordinate for the center of mass y of center of mass, and we can write m1 y1 plus m2 y2. Let us extend it for n bodies. So mn yn whole divided with m1 plus m2 plus mn, and in short we can write summation I equals to 1 to n mi yi and whole divided with this one. Now what about the point masses scattered in a space? So we have three different dimensions now. So we have to add in 3D, we will have to add here another coordinate, and then the same thing will be repeated. So I equals to 1 to n mi zi whole divided with I equals to 1 to n and mi. And here this I equals to 1 to n mi is nothing but sum of all the masses. So we can write it sum of all the masses. Okay. So in this way, we can write what is the position of center of mass. Where is it situated? If we know the point masses and we know their locations. Okay. So up to here, all good. Now, till now we have discussed only point masses which are discrete, means which are separately located. But in reality, we will have some systems where these masses are continuously distributed. Like, let's take an example of thin rod, very thin rod. So, in this rod, the masses, these point masses are not scattered, rather, they are continuously arranged. And we can say that this is a continuous distribution, mass distribution. So, what will be our approach to just find out the center of mass in this case? So let's move ahead and try to find out. Okay, so we have a very thin rod here, This very thin rod is, we are going to treat it as linear mass distribution. Means a continuous mass distribution along the line. Okay, so this is x-axis and this is y-axis. In this case, we are not going to take like M1, X1, M2, X2. This is not going to work here. So what we can do, we can just consider a small element here, very small, infinitesimally small element here. And let's say this mass is small mass, dm. And let's say its location is here at x. So we will have such elemental masses all over, spread all over this length. And now we can do one thing. If we want what is the x cm for this one, we will have to integrate such dm multiplied with x. Better to write in this way. Okay, x cm equals to this one, and whole divided by integration of dm. Okay, this is nothing but the taking limit approach for the same. For example, what we have done, we have chosen elemental masses here, and for all such elemental masses, we have applied this integration concept. So in this way, okay, this is not new. We have already applied such concept. That's why I am not discussing it in well detail. So in this case, we have found out what is HCM. What about this mass distribution is in a plane? That is in case of two dimensions. So the same argument we can extend for Y center of mass. The only thing we need to do, we have to multiply this elemental mass with Y coordinate and then this one. And once again, this integration of dm is nothing but total mass of the system. So here, mass of this thin rod, mass of the system. Okay. So what about in case of three-dimensional body or three-dimensional mass distribution? So for three-dimensional mass distribution, we will have all the three components like x center of mass, which will be this one, and we will have y coordinate for center of mass, which will be this one, and with the same argument, we will have z coordinate, small z here, divided this integral of dm. Okay, now adding vector notations, what will be the scene? So if we are saying that Ri is means position vector for ith point mass in the system, if we are saying this is xi I cap plus yi j cap plus zi, or you can pronounce it as g I k cap. Now this is position vector for ith point mass or ith particle in the system of particles. Now, if we are saying that this is position vector for center of mass, and then we will have x cm I cap plus y, this should be capital as per our notation. So ycm j cap plus capital Z cm k cap. And then we will have a common formula for center of mass. So if we want to write what is the RCN in vector notation, we will have this one RDN. This is for continuous mass distribution, and RCN equals to sum over I equals to 0 to n R, I, and not dA. Rather, here we are choosing discrete masses, so we will have those masses Mi, and then I equals to 0 to M Mi for discrete mass distribution. Okay, keep these two things in mind, and we are going to discuss few examples related to these things so that we can understand these things in a more clear way, and then we will move to motion of center of mass. Okay,